Hello, my name is Uwe Admann. I'm the CTO of Image Engineering, and I would like to give you an introduction into the activities of the IEEE P2020 workgroup. First of all, a disclaimer. Everything I state here, I do in behalf of Image Engineering and our subsidiaries. So I do not represent the entire workgroup, nor do I represent the IEEE. So everything stated here is my opinion, is state what is discussed, but is my personal view, and everything that is in here shall not be related to the IEEE or to the IEEE Standards Association. So this just as a legal disclaimer. So what is IEEE P2020? So first of all, IEEE is an international organization. And within that, we have the Standards Association. So that is a group that is dealing with creating standards. And there we have the group P2020. So IEEE P2020 is basically the name of the work group with a target to develop a standard that shall be released in behalf of this work group and does deal with the the standard for automotive system image quality. So what does that mean? Well, that is a big discussion. So image quality itself is, of course, a pretty wide term, and then also in automotive, this is a pretty wide term. So there is a huge variety of cameras used in the automotive environment that can start from like rear view cameras, which we have already for decades, that can be in-cabin monitoring, that can be advanced driver assistance systems, so forward-looking cameras, surround view cameras, and so on. So there's a huge variation of camera systems in the automotive environment. And I think that is also the kind of a problem of the work group, that the target, the scope is pretty wide. But yeah, so the idea is to have a standard to give people that work in the industry a guideline to work with standards. So what happens right now is if a tier 1 works with a tier 2 or with an OEM, in each project, the image quality parameters, the used KPIs for the project management are defined individually. Each time there is quite a bit of workload on that to define these. And ideally, we would have an international standard so that when you start a project, you can just say, okay, we use these and these settings of that standard, and then everything is defined. That's a target, that's what the work group and also we as active members work on, and it would be great if you could join this activity. So the P2020 community is quite diverse. So you see here images from the meetings. So in the times before the pandemic, we had regular face-to-face meetings around the world, typically around the times when we have also the AutoSense conference. So that could be in Brussels or in Detroit. And but we also met at, for example, Intel in Santa Clara in California. With the pandemic, this of course moved into virtual meetings. So you see some screenshot there. That works rather well. So I think it is productive meetings to discuss online, but of course what's missing also is the community idea. So to chat, to have exchange ideas, and to have just a good conversation with people that work in the industry. So that's why I'm personally looking forward to have personal meetings again. But I think everyone does who is affected by the pandemic. The members, so this is just a small part of the members. So you will see a lot of tier 1s, tier 2s, service providers, and a small number of OEMs. So unfortunately, the OEMs aren't that active in the group. That is more because of considerations that they might get into legal trouble when they work too closely with the other OEMs. At least that's for the German OEMs, I heard. But it is very active from the tier 1s and tier 2s. So there's a lot of members, workgroup members, that are active. As always, there is far more people who are members and who are in the group, who listen, and only a small group that is really active working and is leading the discussions. That is a bit unfortunate, and yeah, it would be great if some of you can also say, okay, I would like to contribute, I have some experience, and it doesn't have to be the full expert in every detail. It would be good to contribute with your experience into the work group. That would already help. So if you would like to become a member, you can freely join the work group, so you do not have to have an IEEE membership. Yeah, you can basically just apply via email. You've seen at the beginning the contact details of the chair and of the secretary. So send an email, say you would like to join, then you can get access to the conference system, so to the discussion system, which is called iMeet. So there's all the files and all the appointments and so on in there. Only if there's the work group meetings, there's a small fee on that, so that the whole work group gets some budget, and the budget is then wisely spent on hardware or on technical editors, for example. But in general, it's yeah, it's basic. It's a pretty cheap way to contribute and to work in the work group. So I think you can much easier. You gain much more than you spend on the small money for the work group meetings. What does the IEEE P2020 try to face? So there is ideally we would like to measure and measure automotive image quality from the scene to the application. That can be a human vision application, so for viewing, like a mirror replacement system or a rear view camera, but also, and very important, for the computer vision algorithm. And that's where we have our challenges. So the environment is pretty wide, so from bright sun to and hot to minus 20 degrees Celsius snow, that shall be somehow covered. We have systems that we don't know in every detail. So for example, the computer vision applications or algorithms are not disclosed, so we don't know in detail what's done there. But also the signal processing in the cameras sometimes cannot be turned off, so it's quite challenging to measure these. And then we have some unique things like that we have to deal with flicker. I'm going to talk about that. So the current situation is that we have drafts for many different image quality factors, so different parts of image quality that have been submitted, that are discussed in the work group. These drafts are discussed and reach a level where we can say we can go for pre-release. So that means that it's not the final standard, but it is. So the idea is to get something out, to get it into hands of external experts so that they can comment on it and that they can give input. So about publications, we hope that we're going to have a pre-release published in 2022. And then based on the feedback and on the continuous work that everyone is working on, that there will be a publication in 2023. So as always, if there are more people that would like to contribute, that work on documents, on research, on validation, the better. So also if you would like to contribute, get in touch with IEEE P2020. Or if you just want to chat a little bit in advance, also you can get in touch with me. Yeah, we can chat how you could help. There is already a document out, so that is the IEEE P2020 white paper that already describes some of the challenges, and that also talks a little bit about the organization of the group. So the different IQFs, or image quality factors, that are considered in the standard are the noise, flicker, contrast detection probability, geometric calibration validation, spatial frequency response, SFR, dynamic range, and flare. So the order here has no intention, so there's no priority. And for all these IQFs, there will be a description how to measure. There will not be a description what is a good value, what is a bad value, because that's something that the user of the camera needs to decide depending on the application. For example, the resolution, you can say for some application having a low resolution is fine because you don't need the details, but for other application, if you want to have a look at a traffic sign in 200 meter, you really need high resolution. So that's why there is no definition what is really needed. So you need some knowledge about your application and about your for example, computer vision algorithms to really make good decisions about what your specific requirement is. Okay, so let's talk about specific IQFs, and as always, I just represent or give you an overview because there is no official release of these, so I take information that is public available, that has been released in some documents, or just to give you an overview. But again, this is representing my knowledge, my state. I'm not representing the work group here, and definitely not representing IEEE here. Okay, noise. So the document that you can refer to is that nicely Orit Skorker and Paul Romanchak, they published at the Electronic Imaging Conference that was held virtually beginning of this year. Normally it's in San Francisco, and they gave an overview, a review of the current status. So that's something that is also open access and is available. So the noise section will cover different IQFs, so small IQFs. So one is dark statistics, so that means behavior of the camera in the absence of light. So you use the entire array, you need no illumination, just dark, and there you can see like dark signal distribution, dark signal non-uniformity, but also temporal components of the noise. This is particularly interesting to really to understand the physics of a sensor, and also this is very interesting to do that temporal depending on the temperature. Especially dark measurements is interesting to measure that at a variety of temperatures. So that's why you should have a look at the climate chamber of image engineering. So we do offer climate chambers specifically designed for the measurement of cameras. So that is also interesting. Then we measure with a transmissive test charts and a backlit source. So that is like a transparent test target. So there's things like system gain, SNR1, effective full well and sensor dynamic range, multiple captures. This is quite low-level measurement, so this is really can be measured for a camera where you have really raw data, sensor-level access. And then the signal fall-off or shading or vignetting is considered here also as a noise. Things that you can observe, particularly in automotive cameras, is you see that in the upper right corner. So these are things, so you see the blue sky, and you see in some region you have quite significant noise, in others you don't. And this is an effect that you have from HDR imaging, so that multiple images are combined into one, and then you have these SNR drops or SNR dips. And this is an effect that you see in many automotive cameras, which you can then also see here, ideally, when you perform the measurement of noise. When you do the dark statistical temporal measurement, you basically capture images in the dark, in the absence of light, and you can do quite interesting measurement there to learn about the cameras, particularly in different temperatures. So you see here junction temperature of 40 degrees Celsius and 80 degrees Celsius, and you see a different behavior of the sensor. So it's particular when you do validations, as cameras have to deal with a huge variety of temperatures in the automotive environment. For the SNR measurement, you use the a transmissive test target with a high dynamic range and different intensities in the back. So these is currently under validation, but as you see, there's quite some measurements have already been done. There are some challenges when you use high contrast test targets, particularly from the lens. So the lens is always part of the system. So you see here that the lens causes some trouble with the reflection of the brightest patches. So that's something where you really need to be careful and need to work on. The target that can be used, or that is used here in this example, is the TE269 C, so a high contrast dynamic range test target, high quality chart, also suitable for infrared, produced by Image Engineering. A suitable light source, because you need a really high power light source, is also shown here, like the LG3. That can be then used for this kind of measurement. The signal fall off or vignetting or shading is also part of that measurement. Here in the document, there is shown that you use a small diffuser and a diffuse light panel, so you do your own setup, and with that you can define the fall off on that measurement depending on the illuminant. So there can be a setup like that if you can validate it yourself. Otherwise, there are of course also other solutions from Image Engineering, like the LE7, a large integrating sphere where you can put also diffuser in, or the small Cal1. The Vega light source, which is also interesting for the flicker measurement that we're going to talk about. And also, if you would like to do these kind of measurements with a large field of view camera, like 180-degree field of view, we also have solutions for that. For example, the Cal3. Get in touch with our team. They are happy to explain and show you more detail. Flicker. Flicker is a problem, particularly in the automotive industry, and that is about light sources that use pulse width modulation. So LED-based light sources that use pulse width modulation for the dimming or for the change of intensity of their light. Things that happen are, for example, shown here in this scene. So you see these traffic signs, so there is an 80 kilometers per hour speed limit in front of the tunnel, and you see that is an active LED-based traffic sign, and it uses pulse width modulation. So the car now captures this like this, and there are many frames in there where there is no sign at all, and that is of course a problem. So your computer vision algorithm will have to deal with that somehow, because there's no way to update these traffic signs. They are out there, they will stay there for quite some time, but also you might have to deal with that in your camera. So to understand from your camera perspective, this issue is very important. The cause is very short exposure times that we have in automotive cameras, and the slow pulse width modulation. Other examples can be that you have headlamps of other cars and they appear like a blinker, so they go slightly on and off, or you have some signage like on the bus that will just show stuff and will not or will make a problem. So the headlamps, for example, is a significant issue because when you're dealing with autonomous driving cars, they might see that as a blinker, or they might confuse that with an emergency vehicle, so that they want to overtake them. That can actually be a problem. Another example we see on the right is for some traffic lights. So if you have LED-based traffic lights, and of course rare, but it can happen, like here, that the camera is exactly in sync with the camera is in sync with the pulse width modulation of the traffic light, and it does not see the red light. I think it's easy to understand that this is a significant security issue. There are different, in the flicker part, there are many different IQFs to measure. So there are different categories as well. So one is the reflectance flicker. So that is more like that you have a light source that is illuminating a scene. You have that like in a parking garage when you have 50 or 60 hertz illumination, or also the headlamps of the car. So if the headlamps of the car use pulse width modulation, which is very common, it can be, and the traffic and the headlamps are the only light source, then you can get these banding effects that you see there. And that is very disturbing, and it can be, if it's really strong, it can also be a significant issue for automatic detection. So, but definitely it is a visual problem for the user. So there are different ways to describe this. There's the flicker modulation index. So when you measure the black parts, it's always about having a gray or a gray target and having light sources that can actually flicker. That's also what Image Engineering is offering. So the light sources that we offer for this measurement can be used for the reflectance flicker, but also for the for other forms we're going to talk about. So these bands, so we have a dark band and a light band, and then the edge rise distance. These are also all measurements that can be performed in this and shall be described in the flicker. So if you really want to go into details, you describe this. Also, what is the other part is the illuminant flicker. So that is when you when you see the illuminant, for example, approaching headlamps or other, and they are flickering, then you can have different HDR artifacts. So you have a combination of flicker issues, and these flickering data goes into the HDR algorithm to combine these, and then very interesting artifacts can happen. So also there we have a flicker modulation index that is working on that. We have the flicker detection index and the modulation mitigation probability. So that is a measurement where you use when you can really describe at which frequency for where is really the problem. So we call that MMP. Or the modulated light mitigation probability. So what you have a light source that is basically turning on and off. So that is an LED light source with pulse width modulation. The camera captures that, and that causes these all kind of artifacts like bands and going on and off and so on. So what we do, or you pick just observe one pixel over time. And if you do that over the frames, you will see that this pixel now, as we have these band effects, will have a high value, will have a low value over time. And now we can check the distributions and compare the distributions. And the closer the distributions to each other are, the less variation we have. And that is something. So you see here, when we have no flicker mitigation, we will have pixel values in the frames high or low. So you see there is some flickering going on. And if there is a good flicker mitigation turned on, so the camera and the sensor does have a flicker mitigation, these values will be on the same level. And that is something that we can describe. And the nice thing is, for this, we can give a value, and we can plot this as a function of the frequency and of the duty cycle. So you can really understand where is the problem of my sensor. So we could identify sensors where we could say, okay, at this frequency, there's no problem, but for these frequencies, there is a problem. So this is something what you can do with the MMP. If you want to do that in the lab, what you need is a light source that you can control very well. And what we use for that is the Vega light source. So the Vega light source is a DC-driven LED light source. So we can have really constant light output from this light source. So no flickering, no intensity change. It is very stable. And it's temperature based, so that we really manage the temperature of it, so it's very stable, it does not change. And on top of that, we have the flicker capability, so we can control the flicker. So we can have different kind of flickers, so that is sine, triangular, and square waveforms. But we can also change the duty cycle, so the time when it's on and off. And we can change the phase information, so we can shift. And that is important. There are light sources out there that can flicker. But you need to be able to control the duty cycle as well, and you also need to be able to change the phase. So the phase means how does the camera and the light source, how do they work to each other? How do they capture? And it can make a huge difference. So you can have in one phase there's no problem, and in a certain other phase there is a big problem as that shifts to each other. So that you really need to be able to measure that. And that is unique for the Vega light source, that you have frequency, duty cycle, and phase shift as possibilities. So the Vega has a control unit, and you can have different sets, so up to 7 light sources can be controlled with that. And then you can have rectangle, sine wave, or triangular kind of flicker that you can control, and in a range of duty cycle, in the certain phase shift, and in a huge range of frequency. And with that, you can also then get huge varieties of different kind of flicker artifacts. So we have seen a lot of interesting things. Of course, this light source is also useful for other things. So you can use that for the MMP, for the flicker, but it is also I think one of the best light sources on the market to do other kind of measurements. You can create a high dynamic range. You have no flicker. So for automotive measurements, also for noise and others, this is really a very versatile light source that can be used for that. Something where it can also be used and where we see example is the contrast detection probability. That is another big IQF in the IEEE P2020. It is under discussion. We will see if it makes its way into the standard and in the pre-release. There are some discussions going on, but it's widely discussed, and a lot of people contribute their research, and it looks very good. So we see that at Image Engineering as a very useful tool. So that's what we understood, and also our customers, where we already did measurements, saw a lot of interesting and really good results, so that they could see issues they have with the camera in the field when driving, that they could also see that in the measurement. And that is, of course, a very good thing. We have, what is the CDP? So basically it's about to give probability how something can be detected. And the ideal approach is that you'd first do a requirement analysis. So what do we really need to do? So here's an example what was done first, and that is what Mark Gese, the mastermind behind CDP, basically presented. So you go out and you define contrast that you need to be able to detect. So for example, if your camera is designed and the only use for the camera shall be the like a traffic sign recognition, you can go out and measure the contrast that you have in a traffic sign and can use that. So your camera needs to be able to detect that contrast. But if it's a multi-purpose camera, and for example you want to detect the cyclist in the dark in front of the dark background, then your contrast is much lower. So then you have other requirements, and your camera needs to be able to detect the contrast between here the cyclist and the dark background. So you can take these samples and you can calculate the contrast. For example, here for the traffic sign you have a huge contrast, for the cyclist you have a small contrast, and that is what you can go use as an input for your CDP measurement, so that you say, okay, this is a contrast that I need to be able to detect. How is that measurement done? So basically it is we just say with the CDP value, we say how well can two inputs A and B be differentiated. So we take two patches here, A and B, they have a certain contrast in the object space, and then we measure how well can the camera distinguish between these two inputs. And so first we calculate the contrast between these two patches, and then we capture data from these patches. So that what happens is, if you capture this, you will have a distribution of digital values. So you have this gray patch, and you have a look, and there will be in this patch, from all pixels that are in this patch, you will have a certain distribution. And then you have two distributions that you have, and then you start to pick values out of these distributions. So you have patch A and patch B, and you just go, okay, take randomly a pixel out of B and randomly a pixel out of A, and from these you calculate each time you calculate the contrast. So that gives you a new distribution. So that means that you have a probability density function of a certain contrast, and then the CDP is basically the area under the probability density function within your within a range that you define. So based on the use case and based on the application, you define, okay, I need to have at least this contrast. This is the contrast of something in the object space needs to have at least this contrast in my image. That's what you define, that's what the boundaries are, and then you calculate, okay, how likely is it that this contrast is really achieved in my camera. So that gives you the bounds, and then you see here, so you have accepted and rejected values, and the more accepted you have, the higher your contrast detection probability is. So now going back, you have two patches, A and B, and for this patch you calculate the CDP. So that means a single CDP value is valid for a given contrast, for a given luminance, and for a certain range or for a certain contrast that you defined. You capture data from a single patch or over time, so that you just take many images, so that you have a large amount of data samples that you can use. So as we said, one combination of like A and B gives you one data point. So now what we can do is we can do that for many different data points. So we can use a lot of different contrast patches and different intensities, so that at the end we're gonna have a CDP map. So this map, so the CDP contrast detection probability is encoded in color. So yellow means 100%. So if you have 100%, it means you have certainty, you are sure that your camera can distinguish these patches, and the lower the value, the lower the probability is. And what we have here in the map is that on the y-axis we have the contrast, and on the x-axis we have the luminance. So what we can see is that the lower the contrast and the lower the luminance, the lower the detection probability. So if it's dark and a low contrast, we cannot really detect contrasts in the scene. And that is something obvious, that is something that we experience as well, but it is very interesting to see that here in the measurement, so that we can also differentiate either different configurations of the same camera, or that we can differentiate different cameras or different sensors. So we see, so that also means if it's very dark but is high contrast, we might still be able to see something to distinguish the patches, but we cannot if it's low light. And so that's how we can interpret that. How does that look in real life? So this is an example. So we have a car in front of us, and of course our visual or the computer vision algorithms need to be able to detect the car. So on the left, there is no problem. So we have clear, the dark and bright has a clear differentiation. We would have a very high 100% CDP. Now there is some flare. So there is some other disturbing light on the lens that causes this flare. And that means that the same region in the object space, so the dark and bright, now get much closer to each other. So the contrast is reduced, and also the CDP will be reduced. And so this is the real world example where CDP gets interesting. So it's not so much about, or it's for the entire system. So here, like this flare is something that the camera does not have under control, but it can happen. And that means that you need to be able also to detect these relatively low contrast. And if a camera does better on this, then this camera has a benefit or is better than the other. So how do we do that in the lab? So as said, we need basically to create two patches, and this is where you see already the Vega light source here as an example. So the Vega light source with these particular test targets is very useful for measuring the CDP, as we can create a huge contrast, huge range of intensities, and we can have a very stable light source. Because we said that we capture images over multiple frames because we need a lot of samples. So if we capture 100 images, we need to make sure that over these 100 images, which can be a couple of seconds to capture, that in this range the light source does not change, or only to a very, very small amount change. And this is what is given with the Vega light source, very stable and very stabilized light source. So that is really important. Okay, so switching gears, another topic, the geometric calibration validation. So what is that about? So the IQF is about the quality of a geometric calibration. So it's not about the geometric calibration itself, because there is an endless possibilities for different models and ways to create these models. And as a work group, we do not want to tell anyone what model fits best for your camera, and because there's also constant development and there might be new models coming out, and we don't want to limit that. So this is about to predict and to say how good is your model, your geometric calibration. So, but just very quickly, what is that about? So a geometric model. So we see here the simple OpenCV camera model, where we have world coordinates, image coordinates, and camera coordinates. And you having the entire model, so a geometric calibration means that we can calculate from these coordinates into each other. So that if I know where my camera is and if I know my image, I can calculate into world coordinates and so on. So this is very important for a lot of applications where you need your camera to give you the image data, and you need to be able to predict, hey, this pixel value is corresponding to this world data or to this data in the world or in the what you're capturing. So there are different ways to do geometric calibration. A very simple one, and I think for the starting point, this is what a lot of people do, can also call it like checkerboard dance. So you have a checkerboard chart and you rotate that in different angles around the camera. So you capture many different images, and then there is, for example, the OpenCV tools. So OpenCV is an open source computer vision library. But these libraries are, so this is also part of MATLAB, for example. So if you do simple calibration for a single camera, this is maybe what you do, or what you can do for a start. There are other ways to do that. Here's an example, see from the website, there's a link there, where there's not a single chart rotated, but there are many charts, and they are positioned in different angles. And so when now rotating the car, you can capture charts in different angles, and from that you can also predict or give the entire model or a geometric calibration model. But both, so having the checkerboard dance, but also having many charts, means that you need a lot of space. And especially when you are in a production environment, space is always expensive, space is a problem. So that's why we have, at Image Engineering, have the GeoCal. So the GeoCal is a system where we use a diffractive optical element to provide a structure from infinity. So that's something that you see below. So that's how the image looks like, that the GeoCal is creating. So a lot of dots, and they all come or originate from infinity. So that means that you can measure a camera even if it has 7-8 meters focus distance, like you typically have for ADAS cameras, and you would need a huge setup in the production line, you can measure here using the GeoCal. It's very easy to have different angles. So basically it's a very compact design. You put your camera in front of the GeoCal, and then you capture an image, and then the software will give you a geometric model. Also here you can have different models defined, so it really depends on the lens design, it really depends on the application, what model fits best. So typically when we get the question, yeah, what model to use, it depends on the lens. So talk to the lens designer, to the team that designed the lens. They should be able to say what lens model or what model fits best for that lens. And then you can use that model to describe. So on the left, you see that is the image, how it looks like. On the right, that is the device. So it's a rather compact design. You can put your camera in front of, and with that, you do a complete geometric calibration. For the geometric calibration validation, according to IEEE, so the document, it's a bit, I would say, scary because it has already more than 120 pages and it contains all mathematical details. So you see a lot of equations in the document. But at the end, what you need is you need a camera system, you need a geometric calibration for that camera. So what kind of model is not limited, but you need a model for that. And then with the measurement, you will tell how good is your model to predict or to predict how the camera behaves. So you need then targets that can be detected well in the camera image, and you need to know their position in the room. So you need to, for example, you have different targets in the room, and then you measure the exact position. So you say they are 2 meters, and basically you say really 2 meters dot 000, so really precise measurement where these dots are or where these markers are, and then you can do different kind of measurements. So that can be a forward projection test and a backward projection test. So basically you use or compare the dots in the image or the location in the image with the location in the field and in the field of view, and that's what you compare. And then you can also do a triangulation test, so where you really have like stereo cameras and try to predict things from that. So yeah, so important. The geometric calibration validation is about validating the model. It's not about creating the model. For creating the model, you have, for example, GeoCal or other methods to do so. Okay, another part, what you do is the spatial frequency response, sometimes also called resolution. So basically what IEEE decided, or the work group decided here, that it's going to be based on the ISO standard 12233, and there particularly the ESFR method, so the slanted edge method. This is not because this is the best for all method, but it's the most versatile method. So slanted edge method has some problems with if you have processed images, if you have sharpening, if you have some form of processing, but in general, it is very versatile to be used, and especially here in automotive, where we have also like large field of view and other application, it was decided to use that one. So the idea or the concept of SFR or spatial frequency response is you obtain the edge spread function. From that, the derivative of that is the line spread function, and the Fourier transformation of that is your SFR, the spatial frequency response. And from this SFR, you can then derive different other KPIs or IQFs like MTF50, MTF10, acutance. So there are different measurements that you can derive from that. There are some modifications to the ISO standard in IEEE P2020. So first of all, the edge spread function, when you get that is, the idea is that you have, or the algorithm says that you first detect the edge, and then you can track the edge and you put all pixels that you have in the region of interest into bins depending on the distance to the edge. And by this approach, you really get a high or very detailed, oversampled edge profile. So a really very good description of how the camera reproduces the edge. What is a problem is if you have some kind of distortion, and basically all cameras do have distortions. And the ISO standard right now says that you should do a linear fit. So you should do a linear fit to obtain the edge position. And that is a problem when you have banded edges, because then the linear fit cannot really describe the exact position of the edge, and your SFR gets worse. So that's why the ISO 12233 will have a polynomial fit of the edge, and as we did not want to wait before the ISO standard is published, the P2020 standard or document will also have this polynomial fit included. But basically it's just a modification of the ISO standard on that. So it will also define positions, where to measure, how to measure, and also define vertical, horizontal, sagittal, and tangential direction. So that is very important because this is sometimes needs some discussion and definitions. So the document will take care of that. The target will be something like this. So basically just slanted edges and gray patches around for linearization. You see here on the right the approach when you have like huge distances and cannot really deal with that, or you have large field of view. So then you can use a single target and rotate the camera. That's also new, so that you do not say we want to have a big flat target, but you say we do have multiple, one chart, and we rotate the camera to measure at the position and field where we want to measure our spatial frequency response. Okay, and then we have another item that is the dynamic range. That is still, under huge discussion, I would say. So we will see what will be part of the pre-release or the release. Basically, it's about dynamic range itself. Is like on the right. If you have a high dynamic range, you can see in the bright and in the dark, and that's something. That's beneficial. You can measure the dynamic range from the sensor itself. That is useful. For that, you can use other measurements, but what we try, or what the authors on the dynamic range here try to achieve, also describe effects of like local tone mapping or global tone mapping and combinations, so to describe halo effects and so on. So this is very difficult to do, and because it is highly depending on the setup, on the target, so what the camera sees, how the camera behaves. So this is really something what still needs a lot of validation. So there is really good approaches under discussion, but there's no so there's nothing very specifically that we can talk about right now. About flare, that's something where we are a little bit more precise. So flare is basically light that is scattering around. So you can have flare can come from internal reflections, from lens elements, from barrels, from bond wires within the imager, cover glass, and so on, so on, so on. So there's a lot of things that go on that can cause these kind of flare effects. There is the ISO 18844 that defines flare as the light that is falling on an image that does not originate from the subject point. That's also veiling flare. In P2020, it is basically all light that reaches the detector that is outside of the optical path. So the P2020 tries to also include ultra-wide lenses and to overcome the problem that ISO 18844 is defined in photometric units, and so that would not be possible to measure in infrared cameras. There are currently two setups defined in the current drafts. So one would be where you have back illuminated test charts and diffusing light. So that looks like this. So you have a transparent target, very bright with dark dots, black dots, and then also have another light sources left and right. For large field of view cameras, the current proposal is to use this kind of huge sphere. It's still a huge challenge to build that as a standard, so that's still under discussion. So you can use, for example, our TE281 for this kind of measurements, or as a custom chart, the 281 as a transparent chart. Feel free to get in touch with our team to discuss details about that, how we can use that. The other setup is a setup B that uses a point light source of collimated light that hits the camera sensor from a certain angle, so that will also scan. The approach here right now is to scan, to move the light source around the camera. I personally think that this is not the best approach. I mean, it's fine to define it that way in the standard, but for the implementation, I think it is much better to rotate the camera, because if you now scan with this light source, you just scan on one dimension. So you just scan all angles in one dimension. But as we know from experience, flare issues can occur from all kind of angles, from all kind of all angles, all distributions, directions, and so on. So it's much better to scan through all kind of directions. Okay, so thank you very much for listening about all the P2020 workgroup content. As right now, my personal view, not IEEE and not the entire workgroup. Yeah, thank you, and we'll be happy to have a Q&A. Thank you.